Bueno, de nuevo, buenos días a todas y todos. Les agradecemos su presencia, su participación. Damos inicio al quinto encuentro mensual del ciclo de seminarios de LLAMA. Como recordamos en cada uno del comienzo de estos coloquios, no está mal repetirlo de nuevo. LLAMA es una iniciativa brasileño-argentina para la instalación de un radiotelescopio en la provincia de Salta, que va a operar en el rango milimétrico submilimétrico. Este proyecto se inició hace unos 10 años y como es de público conocimiento, por lo menos en el ámbito astronómico, tuvo sus idas y vueltas, pero creemos que ahora está encarrilado en su etapa final. Y por eso es que pensamos en iniciar este ciclo de charlas para que los investigadores de distintas áreas de la comunidad astronómica nos cuenten acerca de sus campos de interés, de cómo LLAMA podría ser de utilidad en sus investigaciones. Bueno, como ya es usual, arrancamos con una charla de 40 minutos a cargo de un disertante que estuvo involucrado en el desarrollo del proyecto LLAMA o en el commissioning de algún proyecto de características similares. Luego vamos a tener dos charlas más de 20 minutos cada una y vamos a tener tiempo para realizar preguntas entre las charlas. Para la primera charla, como ya vemos en pantalla, el invitado de hoy es Kauffmann. Vamos a dar una pequeña introducción de su carrera científica. Jens se doctoró en 2006 en la Universidad de Bonn, trabajando en el Max Planck Institute für Astronomía. Realizó postdocs en el Centro de Astrofísica de la Universidad de Harvard y en el JPL Caltech. Entre 2014 y 2017 volvió al Max Planck y de 2017 al presente se encuentra desarrollando sus tareas de investigación en el MIT, como líder de grupo de astronomía del Observatory. Sus intereses científicos son las leyes de formación estelar, las estructuras de nubes moleculares y sus leyes de escala, y la conexión entre la formación de estrellas galácticas y extragalácticas. Para el avance en estos campos se ha involucrado en el desarrollo instrumental en longitudes de ondas milimétricas, submilimétricas y también en el infrarrojo lejano. Actualmente es el PI del proyecto LIGO, Line Emission in Galaxy Observations, en el que utiliza la antena de 30 metros de Sierra Nevada en España para obtener una muestra representativa de nubes moleculares en la Vía Láctea, con observaciones que van de 85 a 115 GHz. También ha sido PI del Galactic Center Molecular Cloud Survey, usando ALMA, CARMA, APEX, entre otros telescopios. El objetivo de este survey fue resolver todas las nubes moleculares orbitando el agujero negro central de la Vía Láctea. Bueno, como vemos en pantalla, hoy James nos va a hablar sobre Wide Field Imaging of Molecular Clouds with Mid-Sized Telescopes. Well, James, we are ready to listen to you.
Okay. Thanks for giving me the, the opportunity to talk here in this forum, and I'm very happy to see such a wide community support the LLAMA telescope. In case you have questions, I'm not very good in looking at the chat window or looking at raised hands, etc. In case you have questions, just unmute yourself and ask, please. That will be the most efficient. And I don't mind you interrupting me at any point. Yeah, let's jump into the talk. So I'm going to talk about wide field emission line imaging with mid-sized telescopes, and emission line imaging meaning here essentially millimeter wave molecular emission lines at roughly 100 gigahertz. So my entire talk essentially focuses on the 70 to 115 or so gigahertz window. So just to set the stage, I'm talking about molecular clouds primarily in my talk here in the Milky Way. And just to set the stage, you can see my mouse, I believe. Can somebody confirm you can see my mouse?
Yes.
Okay, so the clouds have a size of, say, of order 10 parsec, contain several thousand solar masses of gas. They have associated star formation, and then the dense pockets of gas here have densities of order 1,000 or 10,000. Obviously, the density goes higher up, higher in the centers, but the dense gas here is something like 1,000 or 10,000 particles per cubic centimeter. And obviously, there are some ongoing open questions in star formation research, and there are many ways in which you can phrase this. Just to give you some example questions that are relevant for the larger community outside of the star formation community. What's the star formation rate, and how does the star formation rate of the ISM of galaxies essentially emerge out of the ISM physics? And obviously also the star formation process sets the initial conditions for star and planet formation. So this is to say, star formation is interesting in itself, but it's relevant for all sorts of areas in astrophysics. If you don't figure out the star formation process, this is problematic in many areas in astronomy, for many areas in astronomy. And just here to give an example, obviously the star formation process is also relevant for the formation of galaxies. And this is here one such galaxy. And this is actually not an observed galaxy. This is all just a simulated galaxy coming out of the FIRE collaboration. And obviously, all of the distribution of the gas and all of the distribution of the stars you see in this simulation is fundamentally controlled by how molecular clouds form and evolve into star formation. So, yeah, star formation you need to understand in detail in order to get many areas in astrophysics right. So, how can you investigate star formation? So you could, for example, look at infrared images like this one, and infrared images like this show you the young stars, so you can figure those out. You also see here in absorption against the background the dense gas. So you see the molecular cloud as a dark cloud, and this can get you a lot of information, but obviously you can also use a millimeter wave telescope to look at part of this molecular cloud in the molecular line emission. And this is essentially what I'm going to talk about today, and this is my main business at the moment. Here, for example, this is an image from the IRAM 30-meter telescope, multicolor image including the HCN molecule, N2H+ and CH3OH. And so you can study the distribution of these molecules along molecular clouds or within molecular clouds. And there is a lot of structure in molecular clouds visible in molecular emission lines. You see here, I don't know, this is of order 10 molecular emission lines. They all look different. And they all look different because every emission line is slightly differently impacted by gas temperature and density and velocity dispersion, etc., etc. And essentially by piecing the information from the different emission lines together, you can learn something about the gas density of a molecular cloud. You can learn something about the temperature, etc., etc. This is not easy, and actually in some ways how to go from these emission lines to measures of gas density and gas temperature is still many areas in work in progress, but fundamentally the information is there and it can be extracted. And I hope to make that point more clearly later in the talk. This is in particular an excellent tool to study molecular clouds in unresolved galaxies. Here, in this particular image, you can dissect the molecular cloud. You can nicely see this in the core, and you can see the envelope, etc. And you can nicely separate that in terms of space. But if you're studying distant galaxies, this is all just merged into one single blob. And to understand something about the substructure of this blob, you have to come up with smart tools, and using emission lines is one such tool, and it's essentially the only tool that people are using when they, for example, observe molecular clouds with ALMA. So obviously, this community is particularly interested in mid-sized telescopes. Towards the end of my talk, I want to make the point that relatively small or mid-sized telescopes are interesting for some of this work for the following reason. The sensitivity of the telescope is not controlled by the dish size as long as you're looking at extended emission, and molecular clouds are pretty extended. So as a consequence, small telescopes with large beams can provide a very fast mapping speed. And this can be interesting if you want to map large areas. So as I will explain at the end of my talk, mid-sized telescopes occupy a unique and important spot in the imaging speed parameter space. I think this was already explained why I am talking about this topic today. So I am a PI of a large program, the LEGO large program on the IRAM 30-meter telescope. And I'm also the program manager for the Haystack 37-meter telescope here in Massachusetts. So I have both an interest in the science done at millimeter waves, but also the observatory hardware and observatory politics necessary to make such work happening. The LEGO collaboration itself has many members, and so I am relying on a lot of collaborators to present the material I'm presenting today. And particular thanks goes out to a couple of students here at Haystack Observatory who have worked with me over the last 2 or 3 years. So let me give you a very broad idea of molecular clouds at millimeter wavelengths. As you can see in this image, this is the Taurus molecular cloud. This is an image of 12CO emission, carbon monoxide at 115 gigahertz. This is a 100 square degree map. So this is really big on the sky, and this emission is pretty bright at in the 12CO emission line. So it's possible to image large and interesting areas on the sky in this particular emission line. You can also, this is an example of the Orion B molecular cloud, including somewhat more faint emission lines like C18O here, for example. Those are fainter emission lines. And it's still possible to obtain interesting data covering, here in this case, more than a square degree. I think in total this project is going to cover of order 5 square degrees in the Orion B molecular cloud. So it's possible to also not only observe 12CO, but also other fainter species on relatively large scales. Just to give you an idea of the molecular diversity, this is a spectrum between 80 and 115 gigahertz, obtained, I think, with the IRAM 30-meter telescope towards a star-forming dense core. And you see here many, many emission lines, and even if you do an imaging survey where you cover large areas on the sky, you should be able to detect many dozen emission lines from many dozen species if you achieve a relatively modest sensitivity. And as I mentioned, my particular talk focuses on this roughly this spectral range, because if you go to higher frequencies, emission lines become fainter, so it's more difficult to do science. It's still interesting, but it's just you need to observe smaller areas with higher sensitivity. If you go to lower frequencies, there are not too many interesting emission lines. So at around 100 gigahertz frequency, there's a bit of a sweet spot where you can do a lot of interesting science with modest investments of observing time. So this is a star-forming dense core, but you can also observe other galaxies. And so this is, for example, an image, a spectrum taken towards a spiral arm in the M51 galaxy. This spectrum is taken, I think, towards one of these bright spots here. The telescope beam in this case had a spatial size of order 1 kiloparsec. So this spectrum is average of order 1 kiloparsec. And you can now use these emission lines to figure out average conditions of the molecular gas over this spatial scale. You see a range of emission lines, and I've indicated here that some of those emission lines probably are good probes of the dense gas. Other emission lines are probes of the feedback. How is the gas heated by stars? Other lines trace shocks, for example, like spiral arm shocks or so, the formation of spiral arms. That's the idea. So by piecing together the information from all these emission lines, you can learn a lot about the physics in this volume, in this part of the galaxy. So that's one of the reasons why you might want to study galaxies in millimeter emission lines. Very famous work with millimeter emission lines in extragalactic star formation research is the so-called Gao and Solomon relation. Gao and Solomon established that in 2004 or so, and specifically they found that if they observe the HCN luminosity of an entire galaxy, so one integral over the entire galaxy, and then you measure the infrared luminosity integrated over the same galaxy, then you actually get a substantial correlation. The infrared luminosity increases with the HCN luminosity. That's indicated here, infrared proportional to HCN. Then they argued that actually the infrared luminosity is proportional to the star formation rate. That kind of makes sense. Young stars produce luminosity that heats up the gas, and the warm dust then is seen in infrared luminosity. So star formation rate is proportional to the infrared luminosity. And they also made the claim that the HCN luminosity is proportional to the mass of dense gas in molecular clouds in the galaxy. And that is because they say that the HCN molecule is uniquely tied to the dense gas in galaxies. And so then if that's true, then there is this correlation. And if you put both of those together, then you get this proportionality that in the end, this observation, they think, indicates that the star formation rate of a galaxy is directly proportional to the mass of dense gas. But is this really true? Does this in particular hold? So let me reiterate the idea why this proportionality holds once more. So let's think about a molecular cloud like the Horsehead Nebula in our own Milky Way. And because you have high spatial resolution, you can actually spatially resolve the envelope, and you can resolve the dense gas. So you see here it's dense, here in the outskirts it's less dense. You can just separate these different gas volumes in a molecular cloud by imaging it. And for some reasons, the galactic star formation community would in general say dense gas is defined as the mass residing at visual extinctions in excess of 7 magnitudes, roughly. I'll explain that later why that is the case, but that's roughly the rule of thumb that's being used. So what do you do in a galaxy where your beam is so large that, I mean, these are the molecular clouds, you cannot separate envelope and core anymore. So maybe, however, you can hope that you are lucky and there is some tracer molecule Q that only radiates in the dense gas, that's exclusively associated with the dense gas, and essentially means that this molecule Q only emits at densities above some threshold value. And if that is true, then all the dense gas here in these molecular clouds will radiate according to how much dense gas is there. And so then the integrated luminosity of that molecule gives you the mass of dense gas. That's the fundamental idea. As I mentioned before, telescopes like ALMA, and if it's going to get realized, also the NGVLA, whenever they study molecular clouds in other galaxies, they, to a large extent, build on the Gao and Solomon relationship and assume that it holds, and use the Gao and Solomon relationship, specifically the relationship between HCN and the mass of dense gas, to figure out structural properties of galaxies. So that was a primer, general introduction to millimeter wave observations of molecular clouds. So let's now go into some of the open questions. Let's actually go back again to the slide I just showed. So I said that there is the hope that this tracer molecule only emits above some certain threshold density. But how do we actually define this threshold density for a particular molecule? Turns out that this is easy with pencil and paper, but not so straightforward and obvious in actual observations of molecular clouds. Just for background, let's briefly look at definition of dense gas in studies of resolved molecular clouds. A few years back, oh, sorry, I didn't give a reference. This was Charlie Larder in 2010. He came up with the observation that if you count the number of young stellar objects in a molecular cloud, these are all molecular clouds within 500 parsec from Sun, then this number of young stellar objects, essentially obtained from Spitzer observations, correlates with the mass of dense gas in those same molecular clouds if you define the mass of dense gas in these molecular clouds to be the mass of the cloud at an AV in excess of 7 magnitudes. So essentially you draw the AV contour at 7 magnitudes, and all of the mass inside that contour you take as a measure of the mass of dense gas. And if you do that, then you get this nice correlation. And because of that, they came up with the argument that this is a threshold that kind of gives some type of star formation threshold, gives a definition of the mass of dense gas. But now we need to find some equivalent rule for molecular emission lines. And if you use pencil and paper, the intuitive choice is to use a molecule with a so-called high critical density to trace the dense gas. The critical density is, for a given molecule, or actually for a given emission line of a molecule, the critical density is the density above which, by some definition, that molecule becomes very efficient in emitting. It can also emit if the density is below that critical density, but the emission is not so efficient. So the idea was, yeah, we can probably only detect molecules if they are efficient in emitting, so you can use the critical density as a measure for the density which a particular molecule traces. And the particular proposal was to use the HCN molecule, and the because, for example, the 1 to 0 transition at roughly 90 gigahertz frequency has a critical density. Depends on how you define this. The critical density is of order 1 million, but there are optical depth arguments you can use to define an effective critical density which is somewhat lower. So the critical density of HCN, depending on the definition, is 100,000 particles per cubic centimeter, or 1 million or so. So quite high. So now let's look at this in actual observations. So this is data towards the Orion A molecular cloud. This first thing is a dust emission map. And this contour I'm showing here, this is, I think, 5 magnitudes AV. So this is roughly the definition of the dense gas in this molecular cloud. And now I'm having here several emission lines, 12CO, 13CO, C18O, C2H, N2H+, HCN and CN. And you see that some of them here are very tightly associated with dense gas seen in dust. Others are rather extended. And the arrangement of these molecules is not arbitrary, but they are arranged here in order of increasing critical density. So this is low critical density, this is high critical density. If the critical density was the main parameter influencing how molecules couple to the molecular line emission coupled to the dense gas, this should be very tightly correlated with the highest density gas, and this should be particularly should not be very well correlated. And you see that in this range here, the critical density is not the deciding factor. So I would say that this is increasingly accepted in the community, that the critical density is not a parameter that you can easily use to say a molecule traces gas at densities of value X. This is just not how molecular line emission works. For example, because even if molecules are not very efficient in emitting individual ones, if there are plenty of those, then the emission is bright. And this just doesn't make it into those pencil and paper calculations that define the critical density. So now the critical density is not the thing that you can use to say a molecule traces gas at density X. So what can you do instead? So we came up with the following plot. This is again for data in Orion A. Ignore this lower panel for the moment. This axis here is increasing visual extinction. So these are regions of low visual extinction in the molecular cloud, and these are regions of high visual extinction. And here I am plotting now for a given AV contour the fraction of emission for a particular molecule contained in that molecule, or actually outside of that contour. For example, here, to give an example, you take, I don't know, a contour of 10 magnitudes visual extinction, you identify the area, and you measure what fraction of a particular emission line is emitted at column densities less than 10 magnitudes AV. So that you see that depending on the molecule, you have to go not so deep into the molecular cloud to get the majority of the emission, or you have to go very deep into the molecular cloud to get the majority of the emission. And so I am in particular showing here data for the HCN emission line. This is red. And you see that you have to go only to of order 6 magnitudes visual extinction in order to get 50% of the line emission of the molecular cloud. In other words, half of the emission of the molecular cloud in the HCN emission line happens at visual extinctions less than 6 magnitudes. By contrast, the N2H plus emission line is tied much more closely to the densest gas. You have to go out to 16 magnitudes visual extinction to get at least half of it. So this is an emission line which is really nicely tied to the dense gas, or at least to high visual extinction. In this paper, we essentially came up with characteristic density of or characteristic column density of an emission line. The characteristic column density of an emission line is the column density at which, or in terms of AV, at which 50% of the emission line are recovered. So here the HCN characteristic visual extinction is 6 magnitudes, and for N2H plus that characteristic value is 16 magnitudes. Because we are in Orion, we also have a nice density model. And so we can actually associate these column densities with specific densities in the molecular cloud. And you see here that HCN, if you remember, the overall idea is that HCN is typically argued to trace very high densities, depending on the author, 10,000, 100,000, something like that, particles per cubic centimeter. Actually, we find that in this region, it traces densities of order 1,000 particles per cubic centimeter. And, oops, apparently I didn't point that out. N2H plus is a much better tracer of dense gas with a characteristic density of several 1,000 particles per cubic centimeter. Still not very high, but is certainly a better tracer of the dense gas. So that means that it's actually not really so clear to what extent molecules really trace certain density regimes. Let's assume for the moment that you have figured out that a molecule traces a certain density regime. Then you can come up with a conversion relation. You can calculate a parameter alpha, which is the mass of dense gas divided by the luminosity in that emission line. So the idea is you take, for example, here the mass of dense gas from the dust map, and then you measure, for example, the luminosity of N2H plus or HCN, and you divide, you get this alpha constant for HCN or for N2H plus. And once you've done that, then you can turn this around, and for an unknown molecular cloud that you just observed, if you know this constant, and there is a well-established conversion relation, then you can use the observed line luminosity to figure out the mass of dense gas. And this is rather straightforward to do observationally once you have these maps. If you do that, that's maybe what I should point out. I didn't point that out so clearly. This has often been done based on theoretical arguments. But doing this with observational data is in principle straightforward, as long as you have degree scale maps of molecular emission lines. And that's what's really missing. And that's what the point I'm going to make at the end, that your telescope, the LLAMA telescope, would be really great in mapping degree scale emission in faint emission lines like N2H plus or HCN to get those data to actually measure these constants and not only derive them with pencil and paper. So if you do take our best knowledge about these conversion constants, then you end up with the following plot. This is now the mass of dense gas. Here for molecular clouds in the Milky Way, derived from dust emission. kind of with the gold, these are gold standard measurements of the mass of dense gas. The star formation rate you can get from counting young stellar objects or from infrared luminosities. And then I'm putting in here the Gao and Solomon galaxies. And here the mass of dense gas is derived from HCN, where the HCN conversion constant is calibrated in the Milky Way. If I do that, then these galaxies are offset from the star formation relation in the Milky Way by a factor of 5. It's just a small factor. Factor of 5 is not so great in this big in astronomy, but all the errors that I'm making should cancel out here. Yes, maybe this mass of dense gas is wrong by a factor of 3 in general, but then it would be wrong both here and both there. So then all of these data points would either move in this way or the other direction. Here, the same. So those errors should cancel out. And therefore, it seems that this factor of 5 difference is arguably significant. So what does this mean? Star formation relationships are not universal. That could be. You will see that here, these are galactic center molecular clouds. That would be another talk of mine. Those galactic center molecular clouds, they are also not following the star formation relationship that is established in the solar neighborhood clouds. So maybe star formation is just a bit more diverse in the universe than we hope for. Or we just don't understand HCN very well as a tracer of star formation and dense gas. Let me go back once more to this molecular cloud here, and then we already showed you that we have observed this molecular cloud. Let me make once more the case that HCN is probably not so well understood tracer of dense gas. This is, I should have pointed that out, this is one of the standard molecular clouds. This is the so-called the snake. And if you go to star formation conferences, this object always comes up because it's kind of a standard object for a dense molecular cloud at the verge of star formation. And that's one of the reasons why we observed it. And I'm sorry, this is maybe not so obvious here, but the HCN emission in this molecular cloud is really, really faint. This is supposedly one of the dense molecular clouds that we use as a template of a dense molecular cloud. And this thing is faint in HCN, suggesting that HCN is really not such a great tracer of dense gas in general. And so I mentioned that the HCN conversion law is important for understanding the overall star formation rate in galaxies, but you can also play other games that probably shouldn't go too much into the details here given the time. But here, for example, is the HCN to CO luminosity ratio, essentially from a galaxy's edge to the galaxy center. And I should speed up a bit, but the idea is that molecular clouds get denser to the center of the galaxies because CO traces the bulk emission, bulk mass of a cloud, and HCN supposedly the dense gas of a cloud. So if that ratio changes, that suggests that the fraction of dense gas goes up towards the centers of galaxies, as long as HCN is a trace of dense gas. And that actually still needs to be established beyond reasonable doubt. Another thing, back to this cloud G11, the snake, we also have bright emission and HNCO and CH3OH, and those are supposed tracers of shocks. But if you look at the gas kinematics of this cloud, it's not really clear why there should be high-speed shocks of order 10, 20 kilometers per second happening in this molecular cloud. So where is this emission coming from? Probably other production chemistry aside from shocks. But this means that, for example, if you look at other galaxies where this is again a spiral arm in M51 galaxy, CH3OH is often used as a tracer of spiral arm shocks. But if this emission from this molecule is not really associated with shocks, then you cannot investigate the formation of spiral arms with this molecule. Obviously, there are changes in emission, but is it because really there are spiral arm shocks happening in this region, or because somehow the molecular cloud chemistry is changing along the spiral arm? We don't know. This is an example this is part of the work of Amanda Broadmeadow, who looked at some of the LEGO data from my survey. And this is a line ratio where she took the line luminosities of certain various species and divided it by the HCN luminosity, which is just a nice standard to have. And you see there's actually substantial variation by sometimes much more than a factor 10. Meaning, in many of these emission lines, molecular clouds really differ in their emission properties. It's not that if you know one molecular cloud, you know all molecular clouds. Instead, they differ substantially in the internal substructure and chemistry and whatever. And so essentially meaning that this diagram captures and describes that there is a great diversity of molecular clouds in the Milky Way. And you have to understand not one molecular cloud, but you have to understand the population of molecular clouds. If you want to, in the end, reproduce the spectra and line emission observations you observe in other galaxies. This is just another way to visualize this. This is work by Ayush Patel, who's working with me as a very, very bright high school student. And he essentially now doesn't take this line ratio for many lines. So essentially one molecule divided by some other molecule, and then visualizes here now the range of emission between different sources. Sorry, I should have made this clear. Different data points for a given molecule are different molecular clouds. And so this is different because different molecular clouds have different line ratios. Sorry, I think I didn't make that point very well. And here, this is that concept taken to a larger parameter space and showing that whatever line ratio you pick, molecular clouds differ substantially in those line ratios. You can forget about the idea of a standard molecular cloud. They are all different. So let me summarize what are the reasons for pursuing this type of work. There are variations in star formation relationships. We have to understand molecular millimeter wave molecular line emissions in order to place galaxies in diagrams together with galactic star formation regions to understand the star formation process. You have to understand molecular line emission at millimeter waves to understand whether we can really explore density gradients, cloud density gradients inside galaxies. And in general, molecular emission lines show us that there's a great diversity in molecular emission lines. Between molecular clouds, and maybe it's because they differ in the evolutionary stages. And all of this is really relevant for telescopes like ALMA. Let me now finally come to the mid-sized telescopes. So in this image, obviously the dominating thing here is the Milky Way. So what's our overall knowledge of millimeter wave emission from the Milky Way? We all know this nice image of 12CO emission across the sky. But I should point out this is one emission line. This is 12CO. And it's this kind of image is only available for 12CO. No other emission line has ever been imaged this comprehensively. there are now some pioneering projects on the IRAM 30-meter telescope trying to image a couple of square degrees. There's been preliminary, some limited initial work with the FCRAO, the TRAO 14-meter in Korea, and the MOPRA telescope. But all of this is just looking at the tip of the iceberg. And we don't really have anything that resembles a comprehensive view of molecular line emission in the Milky Way. What are the parameters guiding such experiments of imaging molecular emission lines? Well, one obvious one is the beam size, and obviously the beam size of a telescope is depending on the frequency of which you observe and the dish diameter. One thing that's maybe not so obvious is that the received power by the receiver is proportional to the average intensity inside the beam. So it's not directly a function of the dish size. Yeah, a larger telescope will receive more emission from one spot of the sky, but it will look at a smaller area of the sky. And as a consequence, as long as you are looking for extended emission, the power received by the receiver is actually not immediately directly depending on the dish size. These two beams here, imagine you have a large telescope with a small beam and a larger beam with a smaller telescope. Here in this case, the average intensity in these both beams is roughly the same. So both telescopes, though they would be differing in this case probably by a factor 2 or so in their size, would receive exactly the same power. As a consequence, smaller telescopes with larger beams can image extended emission quicker. Simply because if you have such a small beam, you have to generate many pixels across an image to cover the cloud completely. While if you have a large beam, you have larger pixels and you need fewer pixels to fully cover the molecular cloud. And so the mapping speed is different. You could also install on a telescope, instead of one single feed horn, what is usually done, you could install several feed horns and have a multi-beam camera. And obviously this observe many spots on the sky at the same moment, so that speeds up the mapping speed of your telescope. But having more receiver beams is complex. Some telescopes you simply don't have the space to put them, and it's costly. So yeah, it's a really nice way to have more beams, but it's not straightforward. Other thing is, if you want to cover spectral range, you can, depends on how many chunks you have to cover that. Here, for example, it takes 5 chunks to observe these important emission lines. Here, maybe you can do it in 2 setups. And here, if you could maybe also come up with a design with a receiver and backend design that covers all of this in one shot. Obviously, the fewer receiver tunings, and so you have to do separate observings for all of these setups. If you have many such setups, that makes mapping speed slow. So having a large receiver bandwidth and backend bandwidth reduces the number of setups, and that speeds up the observations. But again, it's not exactly, it's costly. It's less complicated, but it's costly. And just to give you an idea, the IRAM 30-meter telescope, which I believe is still the world market leader in covering spectral bandwidth, delivers 16 gigahertz for one single pixel. And going beyond that is costly. So in the end, you cannot come up with a parameter space. So this is the map area that you can cover. This is the beam size of your telescope, which essentially depends on the dish size. I've calculated this here now for 100 gigahertz frequency. And now, if you have a beam size and you pick an amount of time, so I picked here 1,000 hours of telescope time, then you can figure, and you have the number of beams and the number of spectral setups, you can figure out how much area you can cover with a telescope. And you see that, as I mentioned before, smaller telescopes can cover larger areas within a fixed amount of time. Maybe you have not such a great receiver and you have to go through many setups, receiver setups, then you are obviously even slower. Or maybe you manage to have several telescope beams, but again, it's costly to cover bandwidth, so you still work with several setups. So then you, compared to this curve here, you can be a bit faster, but still not so fast. Here for reference are various molecular clouds. And for example, to cover the Taurus molecular cloud, this is an area of several 10 square degrees. And several of these telescope configurations wouldn't be able to cover it. Just for reference, this is what you could do in terms of area coverage with a really, really big ALMA project. ALMA is really good for zooming into details, but not for overviews. Even if you use the ALMA compact array, yes, you can cover more area, but it's still a very small area that you could cover. So ALMA is never going to make any dent into wide field imaging of molecular clouds for various reasons. A telescope like the 100-meter GBT or so delivers fine detail, but it has a bit of a difficulty covering large area. And essentially the same receiver equipment on a smaller telescope would give you much more area. Maybe you could come up with an idea of a dedicated 10-meter class telescope. Dedicated means something like 5,000 hours. Then you could image really, really big areas, and you have to go to projects like this if you want to ever cover something like the inner galactic plane. So that's my message here, that small telescopes fill an interesting, let me summarize this once more here. Mid-sized telescopes occupy a unique region in the mapping speed parameter space. Only small telescopes can go up here. And I would argue that there is plenty of interesting science that can be done in this parameter space, and only in this parameter space. So that actually mid-sized telescopes could have unique, can make unique contributions to this field of research. And I'll leave it at that. Thank you.
Thank you very much for your talk, Jens. Pasamos a la próxima charla, que está a cargo de Hugo Saldaño. Hugo se licenció y se doctoró en astronomía en el Observatorio Astronómico de Córdoba. Actualmente es becario postdoctoral en el observatorio y su campo de trabajo es el de formación y etapas iniciales de estrellas de alta masa. Es profesor ayudante en el Observatorio Astronómico de Córdoba y hace pocos días consiguió el ingreso a la carrera de investigador científico del CONICET por el CCT Salta Jujuy. Bueno, van nuestras felicitaciones para Hugo por el ingreso. Y la presentación de Hugo lleva como título El medio interestelar en galaxias de baja metalicidad.
Bueno, muchas gracias, Germán, por la presentación, por el saludo. Ahí comienzo nomás.
¿Sí podés compartir?
Sí, hay que ir buscando el archivo. Ahí se puede ver.
Está iniciando. Ahí está.
Se puede ver, ¿no?
Sí, se ve muy bien.
Bueno. Bueno, muchas gracias por la presentación, por la felicitación también. Estamos contentos acá de poder haber ingresado a carrera. Y también agradecido por haberme invitado a presentar esta charla donde voy a hablar acerca del área de investigación en el cual me encuentro trabajando actualmente junto con la doctora Mónica Rubio, del Departamento de Astronomía de la Universidad de Chile, que han sido responsables de introducirme en esta área, que ha sido bastante interesante para mí por la complejidad que presentan estas galaxias de baja metalicidad. Para comenzar, voy a ir a introducir un poco lo que es las galaxias de baja metalicidad. Estas galaxias están caracterizadas por su abundancia de oxígeno respecto al hidrógeno atómico, y principalmente van a ser galaxias que van a tener abundancia o metalicidades menores a la abundancia que se mide en la vecindad solar. Simplemente eso. Ahora, ¿qué consecuencias tienen las galaxias de baja metalicidad o el medio interestelar en estas galaxias de baja metalicidad? Yo voy a nombrar algunas de ellas nomás, hay una lista grande, pero solamente me voy a concentrar en algunas de ellas. Los metales son buenos enfriadores del medio interestelar y es lo que se necesita en nubes moleculares para que éstas sean susceptibles al colapso gravitacional, para que se formen estrellas en su interior, ¿no? Como se muestra en el esquema acá tomado de Mote et al. 2018, que es la secuencia de formación de estrellas masivas. Entonces, en regiones de baja metalicidad, este enfriamiento se ve... el medio interestelar es menos susceptible, digamos, al enfriamiento, al colapso gravitacional, y es por eso que se piensa que la formación estelar en estas galaxias sea un poco diferente al modelo estándar que conocemos en la formación estelar de la Vía Láctea. Otro aspecto que tienen los metales es que favorecen la formación de partículas de polvo, y a su vez las partículas de polvo van a favorecer la formación de moléculas. Ahí pongo un esquema pequeño de cómo se forman las moléculas que se forman en los granos de partículas de polvo. Y regiones de baja metalicidad van a tener, se van a traducir en una deficiencia en partículas de polvo y deficiencia de componentes moleculares, ¿no? Principalmente el monóxido de carbono es bastante raro en estas galaxias de muy baja metalicidad. No obstante, el monóxido de carbono es bastante utilizado para trazar estas regiones de formación de estas galaxias, donde el interés es mapear regiones de baja temperatura y baja densidades. Acá presento una tablita pequeña con algunos trazadores de regiones, regiones moleculares, pero nos vamos a concentrar en el monóxido de carbono. Solamente puse el dato de la transición 2.1, que va a ser un buen trazo, va a trazar regiones frías y de baja densidad. Sin embargo, esta molécula, el monóxido de carbono, aún en la Vía Láctea es poco eficiente para trazar el gas molecular, el hidrógeno molecular, ya que se encuentra que el 30, el 50% del gas no es trazado por el CO. Si pasamos a galaxias de baja metalicidad, esa fracción crece considerablemente, entre 80 y 90%. Y acá, muestro acá un esquema de lo que les estoy contando, donde se ve las diferentes componentes moleculares en el medio interestelar y el monóxido de carbono en la Vía Láctea traza una buena porción del hidrógeno molecular, pero cuando pasamos a galaxias de baja metalicidad, esa fracción disminuye considerablemente, bastante. Este es un ejemplo de la nube menor de Magallanes, que es una de las galaxias con la que estamos trabajando y es la que voy a introducir ahora, porque es la galaxia de baja metalicidad, una de las galaxias de baja metalicidad más cercana a la Vía Láctea, ¿no? La primera es la nube mayor de Magallanes. La nube menor, la SNC, se encuentra, aquí puse algunas características, a una distancia de 60 kiloparsec. En la imagen de arriba están las dos nubes de Magallanes trazadas por H1 en contornos. Y abajo la región, la SMC, observada en 160 micras por Herschel. Y en recuadros blancos son las regiones que nosotros hemos observado con APEX. Esta galaxia presenta una metalicidad bastante baja, del 20% de la metalicidad en la vecindad solar. Y por eso resulta que la fracción de gas molecular en esta galaxia sea muy pequeña, solamente del 6% de la masa total. Bueno, observamos esta galaxia con el telescopio APEX en la línea del CO, en la transición 2.1. Acá me voy a concentrar en el bandwidth, que nos va a dar la resolución de observación usando este telescopio y observando esta molécula. Fíjense que es inversamente proporcional a la frecuencia observada. Y acá pongo una lista, digamos, de estructuras que se van a observar en diferentes galaxias, según sus distancias. Y en la SLC vamos a estar observando con APEX, grumos, los clamps, y no un poco más grande. Y también en WLM, que es una galaxia con la que estamos trabajando también, que se encuentra mucho más lejos. Con APEX solo estaríamos observando, bueno, nubes moleculares gigantes. Acá presento un par de imágenes, 2 de 7 regiones que hemos observado con APEX. Es el mapa integrado del monóxido de carbono, donde se indican con elipses las nubes identificadas que hemos podido obtener con CIPROPS, de este autor, Gonçalves, que tal 2006. Y con este algoritmo hemos podido identificar en total, de las regiones observadas, casi 180 nubes moleculares, del cual 70% han sido nubes bien resueltas, es decir, las nubes, el tamaño observado de estas nubes están por arriba de la resolución de observación. Y hemos trabajado con esas nubes. ¿Qué parámetros se miden en estas nubes de CO? La velocidad de dispersión, que me indica el ancho de la línea espectral de la molécula, ¿no? Es un indicador de la turbulencia de la nube. El tamaño, la luminosidad y, bueno, la masa virial, teniendo algunas suposiciones que son nubes isotérmicas, que siguen un perfil de densidad 1 sobre R, y calculamos la masa virial utilizando esa ecuación. Con estos parámetros, lo que se puede hacer es comparar. Si tenemos un buen número de nubes moleculares de una galaxia, lo podemos comparar con las nubes moleculares de otras galaxias de baja metalicidad, que hayan sido observadas con la misma molécula o en transiciones cercanas, en C21 o en C10. Y acá hemos realizado un ajuste de las relaciones de escala de nuestras nubes moleculares del SMC comparada con otras con nubes de otras galaxias. Las líneas de punto en los 4 diagramas representa la distribución de las nubes moleculares de la Vía Láctea. Lo que podemos decir rápidamente de estos esquemas, de estos diagramas, es que para nubes moleculares por arriba de un parsec en tamaño, estas nubes moleculares en galaxias pobres en metales son menos turbulentas que nubes moleculares de la Vía Láctea, de similar tamaño, y también son menos luminosas. ¿Bien? Tienen un desplazamiento hacia velocidades de dispersión más bajas y para luminosidades más bajas, fijando el radio, el tamaño. Y también se observa que si fijamos la velocidad de dispersión, las nubes moleculares en estas galaxias pobres en metales son más luminosas, ¿no? Tienen esa contraposición entre la luminosidad y el tamaño, y la luminosidad y la velocidad de dispersión. Si nos vamos a escalas más pequeñas, en nubes moleculares dentro de estas galaxias pobres en metales, como se muestra en los puntos grises, de la región de 30 Dorado, que es una región con formación estelar muy activa, se observa que el comportamiento es bastante diferente, el corrimiento, el desplazamiento respecto a la distribución de la galaxia, de la Vía Láctea, es en dirección opuesta al resto de las moléculas de mayor tamaño. Esto principalmente se debe a que nubes pequeñas están directamente o están mayormente actuando con regiones de formación estelar, entonces son nubes más perturbadas, por lo tanto van a mostrar mayor turbulencia, una mayor luminosidad con respecto a sus contrapartes de la Vía Láctea. y de regiones de nubes moleculares de galaxias pobres metales, también observadas, que tienen una actividad estelar muy baja, ¿no? Como los cuadrados en rojo del puente magallánico, ¿no? Pero ese corrimiento, ese desplazamiento respecto a la distribución de la Vía Láctea, en la luminosidad radio y en la luminosidad dispersión de velocidad, aunque sean direcciones opuestas, esos desplazamientos se cancelan cuando calculamos la masa virial y comparamos con la luminosidad, y vemos que todas las nubes, independientemente de qué galaxias sean, de qué actividad de formación estelar presenten, van a caer en una banda bastante definida, parecida a la banda de la Vía Láctea, y aunque están un poquito más inclinadas, ¿no? Esas son algunas características que se pudo encontrar en estas galaxias pobres en metales con respecto a la Vía Láctea y en comparación entre ellas. Otra cosa que podemos hacer, y es lo que también estuvo explicando Kauffmann hace un momento, es sobre el factor de conversión que se suele utilizar mucho en la literatura para convertir la luminosidad, en este caso del monóxido de carbono, a hidrógeno molecular. Nosotros, teniendo una muestra considerable de nubes moleculares en la SNC, pudimos estimar este factor de conversión para la galaxia utilizando dos métodos. El primer método utilizamos el método virial, donde se asume que las nubes moleculares están aproximadamente gravitacionalmente estables en condición virial. Por lo tanto, podemos asumir que la masa virial que nosotros medimos con las emisiones de CO está muy próximo a la masa del hidrógeno molecular de las nubes. Y eso lo hicimos con todas nuestras nubes y lo indicamos acá en este esquema, en este diagrama, donde tenemos el factor de conversión en función de la luminosidad, indicado en puntos grises. Y vemos que se distribuyen de manera uniforme, no hay una dependencia con la luminosidad, a diferencia de lo que sucede con las nubes de la Vía Láctea. Y encontramos un valor medio de 14,5. Acá no pongo las unidades porque si no me llenaría de letras y sería bastante confuso. Pero después utilizamos un segundo método, un método más preciso, porque utilizamos la emisión del polvo. El polvo tiene mayor capacidad de trazar el hidrógeno molecular en regiones más extensas, porque tiene esa capacidad de absorber la radiación ultravioleta. Y vamos a utilizar esta aproximación para la masa del hidrógeno molecular de las nubes, teniendo en cuenta las mediciones de la masa del polvo. Para eso utilizamos la masa de polvo medida por Takekoshi en el 2017, que modeló la distribución espectral de energía a una resolución similar a la nuestra, a nuestras observaciones en CO. También utilizamos un factor de conversión tomado de literatura, que ronda estos dos valores, para el SNC. Y teniendo en cuenta el trabajo de Jameson 2018, podemos ver que se puede ver que en regiones donde el monóxido de carbono es muy brillante, la componente de hidrógeno atómico es casi despreciable a la masa de hidrógeno molecular. Por lo tanto, ese término lo podemos despreciar por ahora, hacer una primera aproximación, para poder estimar ese factor de conversión. Y usando este método encontramos que es un poco más grande, mucho más grande, 9 a 18 veces más grande que el valor canónico adoptado para la Vía Láctea, ¿no? Está acá indicado en esta línea horizontal. Y eso es de esperar, porque obviamente el polvo va a trazar mayor cantidad de hidrógeno molecular, por lo tanto va a tener mayor cantidad de masa que vamos a estar midiendo para la luminosidad que nosotros hemos medido mediante nuestras observaciones, y eso hace elevar el factor de conversión. Esto es bastante consistente con resultados que se encuentran en la literatura, ¿no? Acá muestra un esquema de Hirashita y Harada de 2017, que grafica el factor de conversión en función de la metalicidad y modela este parámetro, donde se ve que el factor de conversión va a crecer hasta 2 órdenes de magnitud para metalicidades muy bajas, ¿bien? Nosotros, el factor de conversión que calculamos nosotros está en este rango, de que yo indiqué con una banda oscura, que es bastante consistente con las observaciones y con este modelado. Después, paso a explicar un poquito de lo que conocemos de otra galaxia, conocida como WLM, que es una galaxia mucho más, con una metalicidad mucho más baja que el SMC, en 13% de su metalicidad. Es una galaxia que se encuentra mucho más alejada, que en un principio, por su baja metalicidad, no se podía detectar emisión de CO en estas galaxias, y se pensaba que este límite de metalicidad del 13% sería efectivamente un límite a partir del cual ya no se podría observar el monóxido de carbono para metalicidades más bajas. Después el MEGRIN en el 2013 pudo detectar con APEX la emisión del CO en la transición 3.2 en estos 2 puntos que estamos indicando acá. Y acá a la derecha se ve la emisión del CO bastante débil en comparación con la emisión en H1. Ellos estiman que la fracción de CO en esta galaxia es aproximadamente un 3% de lo que obtenemos en la Vía Láctea, bastante poco. Abajo tenemos la misma galaxia observada en H-alfa, ¿no? Regiones de emisión, donde los recuadros indican las regiones de donde se observaron con ALMA esta galaxia para identificar la emisión de estas nubes moleculares a través del CO. Bueno, acá tengo unas características de ALMA. Me voy a concentrar solamente en el bandwidth, que me va a dar la resolución, y no depende solamente de la frecuencia que vamos a observar, sino también de la línea de base, del baseline, que me indica que es la máxima extensión del arreglo de las antenas utilizadas. Y acá una tablita pequeña para 2 tipos de línea de base, 160 metros y 16 kilómetros, que es la máxima, creo, que se quiere alcanzar con ALMA, y los tamaños que se estarían observando en las diferentes galaxias que estoy presentando, en SMC, en WLM. En WLM, con ALMA, se espera una resolución de 0,02 segundos de arco, poder medir tamaños de la décima del parsec, que sería un logro bastante grande por la complejidad que tiene esta galaxia. En el Rubio, tal 2015, pudo identificar con ALMA, no puse acá la molécula, pero es el CO transición 1,0, se pudo identificar hasta 10 nubes moleculares pequeñas en las regiones que se están indicando acá en el recuadro. Las nubes están indicadas en negro, en puntos negros, son muy pequeñas. Y acá un zoom de esas regiones donde está la nube en color con sus respectivas líneas en CO. Y se ha observado esta galaxia en una resolución de 1 segundo de arco con ALMA, que equivale a 5 parsecs en diámetro. Actualmente nos encontramos trabajando con nuevas observaciones de ALMA en esta galaxia, que ahora se ha mapeado esta galaxia en CO21, una región mucho más grande de la galaxia, y se ha podido identificar hasta 35 nubes moleculares pequeñas. Hay 12 nubes moleculares que son candidatas, tienen emisiones bastante débiles, así que hay que saber si son realmente nubes moleculares. Y lo interesante de esto es que a este grado de metalicidad, un 13% de la abundancia solar, el monóxido de carbono es prácticamente inexistente en esta galaxia. Para metalicidades más bajas, el monóxido de carbono sería casi difícil de observar. Bien, esto es lo que venimos haciendo trabajando con galaxias de baja metalicidad, principalmente el SMC WLM. Y ahora la pregunta es, ¿qué podemos hacer con llama? No voy a hablar, voy a concentrarme en algunos detalles. Sabemos que una antena va a ser una antena similar a ALMA, a una de las antenas de ALMA. Pero lo que me quiero concentrar ahora es que LLAMA, ubicado acá en cercanía de, bueno, el departamento de San Antonio de los Cobres, va a tener una distancia de 180 kilómetros a la ubicación del telescopio ALMA. Y la idea es poder combinar LLAMA y ALMA para obtener observaciones de una resolución mucho más alta de la que venimos trabajando, incluso con ALMA. Trabajando con LLAMA solamente, observaríamos tamaños similares a lo que observamos con APEX, ¿no? Un single dish. Pero combinándolo con ALMA, la resolución espacial aumentaría considerablemente y estaríamos observando en la SMC y en WLM estructuras muy pequeñas, los cuales nos favorecerían mucho para entender varios aspectos que voy a nombrar ahora, algunos de ellos. Primero, con LLAMA, con solamente LLAMA, vamos a poder seguir aumentando la muestra de galaxias pobres en metales, bien que se encuentran en literatura, muchas de ellas que todavía no están siendo estudiadas, para poder comprender mejor cómo es el medio interestelar en estas galaxias. Acá presento algunos ejemplos nada más, donde fueron observadas, donde se observó el CO, pero en regiones puntuales, no se mapearon estas galaxias. Y después acá hay una muestra de más de 40 galaxias pobres en metales. Solamente muestro 3 que fueron analizadas en el infrarrojo. Y sería interesante poder observar con LLAMA mapear estas galaxias con LLAMA y poder analizar el medio interestelar. Lo otro que para mí sería bastante interesante, como le dije anteriormente, combinar LLAMA con ALMA para poder observar estructuras mucho más pequeñas en estas galaxias de baja metalicidad y poder aumentar, digamos, el conocimiento en cuanto a la formación estelar en esta galaxia. Le había dicho al principio que la formación estelar en este tipo de galaxias sería un poco diferente a lo que conocemos en la Vía Láctea, por lo que sería interesante mapear observar estas galaxias en escalas de la décima y la centésima del parsec, ¿no? Con esta combinación de ambos telescopios, y poder observar lo que observamos en la Vía Láctea, núcleos moleculares muy pequeños, agrupaciones de esos núcleos, o incluso poder ver cómo el comportamiento de los flujos moleculares, de los outflows y discos, que no indican la presencia de formación estelar. Otra cosa que sería interesante poder utilizar en la combinación de estos telescopios es poder analizar las relaciones de escala que le había explicado anteriormente, pero extendiéndonos a escalas muy pequeñas, de la décima, la centésima, incluso por debajo de esa escala, que si bien se viene haciendo con ALMA, combinándolo con LLAMA podríamos irnos un poco más abajo en la escala y poder analizar estas relaciones para poder analizar la dinámica de las nubes moleculares, el comportamiento que tienen en las galaxias pobres en metales, y acá podríamos compararla con relaciones de escalas similares que se vienen haciendo en la galaxia en escalas muy pequeñas, en la Vía Láctea, en estas escalas muy pequeñas. Bien, eso en resumen, digamos, fue lo que venimos trabajando y lo que esperamos hacer y trabajar con LLAMA.
Bueno, muchas gracias por tu presentación, Hugo. Y pasamos a la tercera charla a cargo de Thiago Signorini Gonçalves. Thiago se licenció en Física en la Universidad Federal de Río de Janeiro. Hizo un máster en Astronomía en el Observatorio Nacional y se doctoró en Astrofísica en Caltech en 2011. Realizó un postdoc en la Universidad Federal de Río de Janeiro, donde es profesor adjunto y docente de posgraduación. También fue profesor visitante en la ESO, en Chile, y actualmente es el coordinador del Grupo Científico de Trabajo número 3 del instrumento Mosaic, un espectrógrafo multiobjeto para ELT. Su línea de investigación es la formación y evolución de galaxias, estructuras en gran escala en el universo e instrumentación astronómica. Bueno, la presentación de Thiago lleva por título The Physical Conditions of Molecular Gas in Low and High Redshift Galaxy. Muy bien, Thiago, te escuchamos entonces.
Ok. Bueno, buenos días a todos. Bom dia a todos no Brasil. I can speak English and Portuguese. I'm probably going to switch to English for the talk itself, but feel free to ask me in any language you prefer. And I would like to thank the organizers of this series of talks for the invitation to discuss a little bit my work here. And also, I would like to thank the previous speakers, Jens and Hugo, because they introduced the topic very well. Especially Hugo talked a lot about the low metallicity end of gas studies, of molecular gas in particular. I'm going to talk a little bit. Actually, I'm going to talk a lot about that, and it's a great introduction. So there are a lot of things that I can actually speed up because Hugo gave us very nice introduction on the topic here. I'm just gonna maybe extend that idea a little bit further down to higher redshift galaxies. So first of all, of course, I should thank all of my collaborators here. This is project that has been going on for a while, as you're gonna see, and many people are involved, people from Brazil and other countries as well. This is probably one plot that you're going to see a lot in many talks about high redshift galaxies. The main idea is that the speed with which the universe is forming stars has varied a lot in the past. We don't know really well how that actually works down to redshift 8, 10, or maybe higher. We're probably going to learn more once James Webb is launched. But we do know for sure that there was a really strong evolution in the volumetric density of star formation in the universe since redshift 2 or so, or in the last 10 billion years. And the universe was forming stars much more rapidly in the past. That in great part is due to the evolution of galaxies themselves. So when we compare the properties of individual galaxies, especially at a given mass, the galaxies were forming stars much more rapidly. So galaxies of a given mass, 10 to the 10th or 10 to the 11th solar masses, they were forming stars at a much faster pace at redshift 2, for example. So this is a relation between stellar mass and star formation rate that evolves very strongly. But at the same time, there are galaxies that are not within that main sequence of galaxies. Some galaxies, which we call starbursts, and this is just one example from Julia Rodriguero and collaborators in 2011. Some galaxies are more efficient in forming stars for a given stellar mass, and one thing we would like to know is why that happens. At the same time, we also want to know why galaxies were so different in the past. First of all, we do know at this point that they had more gas, even when you take out the bias you might have in terms of observability of gas at high redshift. And at the same time, we do know that galaxies were more metal poor, which is somehow to be expected because they didn't have as much time to form the atoms of the more metal rich elements, the metallic elements, carbon, oxygen, and so forth. So galaxies in the past were more metal poor. And that, of course, affects us, as we have seen what Hugo said. This affects a lot how galaxies might process their gas and how they might form stars. The problem is that the studies at high redshift are really difficult because, of course, you're looking at large distances, and the luminosity distances are large. They're going to be faint objects, and at the same time, if you want to do resolve studies, there's going to be really intense surface brightness dimming, meaning that any surface brightness effects that you're going to look for, they're going to be much fainter, and especially the outskirts of the galaxies are much harder to look at if you want to resolve all the galaxy. So one thing that we have been doing for a little while now is to study local analogs of high redshift galaxies. Nowadays, this is actually a really popular topic. People have been using green peas and the LARS sample. There are a few samples like that look at different types of analogs. We have been playing that game for 15 years now. The first paper was by Tim Heckman in 2005 from Galax data. And this sample in particular is at redshifts 0.1 to 0.2, more or less. And the selection here is done essentially by ultraviolet luminosity and surface brightness. We have done many studies by now to show how this analogy works. This plot here on the right is, on the left is one of my favorites because it's the relation between bolometric luminosity and infrared excess. We see that for local galaxies, the small black dots and the circles, the magenta circles, there is some type of relation between those quantities. But when you go to higher redshift for a given infrared excess, for example, you have much higher bolometric luminosity, or for a given bolometric luminosity, you have lower infrared excess. And those are the blue triangles in that plot, and our sample of analogs is the big black circles. As you can see, they resemble much more the high redshift galaxies than any type of local galaxy. This is work done by Roger Coverzier in 2011, and we've been studying the metallicity, the mass metallicity relation, as you can see in that plot with the colored circles there, especially the colored circles. And we see again that those galaxies are more metal poor for a given solar mass. There are many plots like that. I'm just showing a couple here. But indeed, they can be classified as Lyman break analogs, the LBAs. This is a sample that we have been studying for a while. As I said, this is work that I've done for my PhD. So, for example, when we study the kinematics of the ionized gas, we see that these galaxies have properties that again are very similar to actual high redshift galaxies. There's a whole paper on that. I can give you more examples later if you want, but here the idea is just that they compare very well. But what I want to discuss here is, again, the properties of gas. I mentioned earlier the fact that these galaxies are more metal poor, and there's this huge uncertainty, especially when you go to really low metallicities about the alpha CO factor. You've seen in Hugo's talk that can vary by quite a bit. And again, for high redshift galaxies, that is also a big unknown if you want to study the properties of molecular gas. You've seen something similar to this already, so I'm going to go fast here. But again, the idea is that you have some sort of UV radiation field, especially if you have a region of star formation with very young stars, very massive, a lot of UV radiation that might destroy the CO, and the CO is only found in the very inner parts of the cloud. It is optically thick, so you're only seeing the surface of the cloud, the surface of the CO emitting cloud. You're not seeing all the way in, but there's actually a good relation for most regular normal galaxies between CO luminosity and the virial mass. So we can use that for normal galaxies. So what happens exactly at high redshift? Why do galaxies have more gas? What exactly is going on? And in particular, one thing that interests me is whether these galaxies are more efficient in using their gas to form stars, or if it's just a matter of having more gas in them. So this is something that I started doing a little later. This is something that I've done with Karma, looking at some of the galaxies in our sample, looking for CO 1 to 0 emission in these objects. And we've seen that, again, the fraction of the gas fraction, the baryonic fraction of mass in the gas is really high, up to 2/3 more or less. That varies a little bit with the stellar mass of the galaxy. But as you can see, that yellow bar there shows the typical values in the local universe, and these galaxies are much more metal rich, and they're very similar to actual galaxies at high redshift, which are the other circles there, and the theory that is shown in gray. So yes, these galaxies, again, they resemble high redshift galaxies in the sense that they have more gas. They have a really high fraction of baryonic mass in molecular gas. But when you compare let's say the efficiency given by the Schmidt-Kennicutt law, which is the surface density of star formation versus the surface density of gas, this has been done by many people, and we have found that, especially if you take a look at the blue circles there, which is the work that we've done, these galaxies are indeed on, let's say, the main sequence of star-forming galaxies. They have a relation that is very, very much in line with normal spirals. When you compare these two quantities, they're just at much higher values for surface density than spirals. So they're much more compact, but the relation between star formation and gas seems to be the same. They're not like starbursts, like Eulergs or the sub-millimeter galaxies, nothing like that. They're more like normal galaxies, which is shown again by especially the high redshift normal galaxies are all that red and orange symbols around there. But these, we could only observe the more massive galaxies and the more metal-rich galaxies in our sample. So what happens at low metallicity, if you think about it, Hugo talked about that as well, but if you think about it, there's a problem. If you go to low metallicities, you have lower dust abundances, and the UV radiation can more easily penetrate the cloud and break up the molecules. But at the same time, if you go to very turbulent galaxies within the local universe, for example, the Eulergs, the alpha CO goes the other direction. It is more intense because supposedly the turbulence in the gas excites those molecules, and it can drive up the CO luminosities, driving down the alpha CO values. This is something that has been, especially the low metallicity thing, is something that has been explored a lot lately. This is work done by Susan Madden last year. And for example, if you look at C2, which is what you would get if you dissociate the CO molecules, you might get a higher abundance of C2 with respect to CO. And as you can see, the dwarf galaxies, which are the more metal poor galaxies in the local universe, they are at much higher values at that fraction. So if you look at the dashed lines, for example, which are different ratios between C2 and CO, the red points are at much higher values, meaning probably, yes, the UV radiation is penetrating more and driving down the alpha CO value, sorry, driving up alpha CO and destroying the CO molecules. And C2 is very popular nowadays for studies at high redshift. It's very convenient for ALMA because it's redshifted into easy to find bands. And lately, people have been using O3 as well. The idea is more or less the same, that you dissociate a lot of the molecules and you excite them. So they are very bright in O3. This is just one example by Harikane in last year as well. But O3 again is becoming very popular for finding molecular gas. At high redshift, the problem is inferring the total amount of gas from those measurements, which is not trivial. So what we try to do, and this is data that we've already had. I'm just trying to publish this now, but I'm doing here some. This is what we expected earlier for the entire sample of analogs, to estimate the CO luminosities if we have on the left a constant conversion factor, constant alpha CO, and on the right if we have lower metallicity conversion factors. So of course the CO would be much less luminous for the less massive galaxies. And we went ahead and tried that with a few galaxies in ALMA, looking for CO120. And lo and behold, we have not detected any single emission in CO120, even with ALMA. And this is very robust in the sense that these objects are far below the typical relation between CO and far infrared. So indeed, yes, the CO, these galaxies are CO dark in the sense that molecular gas is very hard to find in these objects. But we can do some sort of correction for metallicity, even for the far infrared luminosities. We corrected that a little bit. And then we take those four non-detections, and the idea here is just that CO luminosity is corrected for that metallicity factor, and that seems to work very well in the sense that they are back on the relation. The idea here being that if you take into account those metallicity factors, that seems to explain everything pretty well. And they get back on that relation there. The problem is that there seems to be no turbulence effect. These galaxies are very turbulent, but it seems that at least within individual clouds, that turbulence for these objects does not seem to play a significant role. So this takes me back to an interesting paper by Mark Krumholtz and collaborators back in 2012. They were trying to do this universal Schmidt-Kennicott law relation between star formation rates and gas, and they wanted to include even the GMCs, the giant molecular clouds themselves, into that relation with also the galaxies, assuming there must be some sort of universal law for the whole thing. And yes, we know that this does not work. But then what if you include the orbital time, the rotation time of those objects? That's even worse. So clearly that does not work at all. But then what if you include the free fall time of the gas in those objects? And yes, that seems to work well. So you can unify clouds and galaxies and all of that into one single relation between star formation and gas, if you divide the gas by the free fall time. The trick here, and this is not very easy to explain, is that you're using different free fall times for different objects, not just different galaxies actually, but different objects altogether, because the low redshift galaxies and the GMCs themselves, they use the free fall time of one individual cloud, assuming that the clouds in galaxies like the Milky Way, for example, they're detached from the rest of the ISM, so they're self-gravitating and they're self-governing. They don't care about the rest of the ISM. Whereas the free fall time for high redshift is governed by the tumor regime, at least in this paper, in the sense that they're not separated from the disk, but the whole disk is this kind of fluid with a lot of molecular gas within the disk itself, and it's fragmenting due to ternary fragmentation of the gas while it's rotating. So the free fall time there is completely different. It's a different regime, and that's what governing, at least according to this paper, that would be governing the star formation activity there. So what we did later, again, this is some ALMA data that we got, is what if we can probe the star formation within a galaxy? And I took advantage that I already had the emission line with adaptive optics from Keck at the time. This is from my 2010 paper. And we went ahead and probed one galaxy, but in very high resolution with ALMA, around 0.2 arc seconds. We do see some clumps of star formation there. We can identify those. And we can measure, for example, the surface density of star formation rate. This is very high. And what I want to show you here is comparing the maps. The left is Passion Alpha. I switched the colors there, I'm sorry. But the left there is Passion Alpha, so hydrogen ionized emission, star formation. And the left is for ALMA CO3-2 now. And when we combine the two, so we can divide one by the other, and we have a measurement of star formation rate within the galaxy. And as you can see, the center of the galaxy is much more efficient in forming stars than the rest. And that is by the whole thing. Of course, the point here is that you need ALMA because the whole thing is approximately 2 arc seconds across. The circle there is more or less the beam size of ALMA. But when you compare the two, each point in that plot is a single pixel, the star formation rate versus CO as a function, either of star formation rate or CO. And as you can see, the central points and the clumps themselves, not just the central region, but the clumps themselves, they are more efficient in forming stars, sometimes by a factor of up to 4 to 5. So it's not just a matter of fragmenting in terms of ternary, in a ternary regime for the whole galaxy, but the clumps themselves seem to be doing that at a different rate. And now just to wrap up, I'm going to comment that can we use other diagnostics to do that sort of work? And for example, this is something that Nick Scoville did in 2016. He has used ALMA a lot to do that at high redshift. This goes out to redshift 4, as you can see. And according to him, a lot of the increase in star formation efficiency is due to higher gas fractions in galaxies that are above the main sequence. So Star formation rate above the main sequence is on the y-axis for all plots there, and the x-axis is just the stellar mass. As you can see, the galaxies that are far above the main sequence supposedly have more molecular gas, but that is not exactly found by everyone who does that with CO. The whole thing is very complicated to do. So we have a lot of different diagnostics there. One thing that we're going to be able to do, and this is, some of you may be familiar with this project, this is the TOTAC instrument that's going to be installed at the LMT in Mexico. It's an array of kinetic inductance detectors. They have dichroics that separate the emission in different bands. So you're going to get pretty much every band at once in different detectors. It's super efficient at mapping, especially. And so just so you have some numbers here, this is what the mapping speeds that you're going to get at different bands between 1 and 2 millimeters. And especially there's already a survey that's being designed, a 100-hour survey, that's going to map approximately 1 square degree in the sky, which is more or less the size, let's say, of the cosmos field, a little bit smaller, but it's going to go down to 0.02, like 20 microjanskis, more or less. So 0.02 millijanskis. It's going to be really deep, and because of negative K correction, we're going to be able to see dust emission all the way to redshift 8. But again, these are different methods of looking at things. I would say the jury is out there exactly on how galaxies at high redshift process their gas. And I don't have any specific slides here about LLAMA, but certainly I've given this a lot of thought. LLAMA is not going to be as sensitive as a 50 meter antenna or ALMA, of course, but I think LLAMA could really help in the sense of giving some sort of complete survey, at least, let's say, a volume limited, mass limited sample of galaxies. That goes very much hand in hand with what Hugo was saying about a survey of local galaxies, metal poor galaxies. We can see how deep and how far we can go. I don't know the numbers off the top of my head, but I think if we had some sort of ambitious program that has a comparison, we would have to check also what kind of bands we would have available for that sort of studies. Certainly the high frequency bands would be good for the dust emission, because the dust is bright at like far infrared bands. But I think it would be really nice to have some sort of complete sample, not only of the dust emission in the continuum, but also some emission from molecules. We heard a lot about from Jens of high density tracers. It would be really interesting to do that in a sort of complete way in a number of galaxies at low redshift, and have some sort of anchor in the low redshift universe that we could compare to high redshift and try to see what we would actually expect. Because at high redshift, of course, there are many studies with ALMA by now, but I think some sort of survey, some sort of complete survey at low redshift could really help guide studies at high redshift, and we could understand much better the formation of stars and the processing of molecular gas, and especially in such weird environments, sometimes turbulent, but certainly the metal poor environments, which are still poorly understood, in my opinion. So I'm going to thank you here, and I'll take questions. Thank you very much.
Thank you very much, Thiago, for your talk. Damos por concluido el quinto encuentro de ciclo de seminarios LLAMA. Nos volvemos a encontrar, si no me equivoco, el 5 de noviembre.